So good morning and welcome back, and this is the second video lecture. So in the last class, we have seen the two classification of signals, that is analog signals and digital signals. And I told that analog signals are naturally occurring signals. So their base is time. So the independent variable is time, the x-axis is time. But digital signals are very simple, but they are not a ready-made signal. They have to be converted into digital signals by sampling and A to D conversion. And we have seen that instead of time, the base is small n, which is simple numbers. Numbers also in the sense that are integers. N is an integer. So I'll tell the reasons of all those things later in a little bit later stage. But time being, just understand n is a simple integer. We have seen several examples. We have seen that n is an integer. N can be a negative number or a positive number, even it can be 0, but they are integers, invariably integers. And one more thing is that, see, the spacing. See, n is equal to 0, the next value is n is equal to 1, and the next value is at n is equal to 2. The next value will be n is equal to at n is equal to 3. So you can see that the spacing is even, the spacing is same. Okay, the naturally a question arises, can't the spacing be different? Yes, of course, the spacing between the values can be different also, but that makes the system more or less complicated. Why should we make the system complicated? So we are trying to make the system simple, and the spacing between the samples are the same, and n is invariably taken as integers. So today we'll see few elementary signals. So you can see that the 7 types of elementary signals. You can go through it. We will see each of these elementary signals one by one. Okay, so the first one is a unit step function. So parallelly we'll see analog step function as well as digital step function. For all the elementary signals, there is analog signal as well as digital signal. So parallelly we'll see both. So first we'll see what is a unit step function. So we'll just go through the first definition. First we'll see what is an analog step function. So the representation, the symbol of a unit step function is u of t. So while you see inside the parenthesis you see the t, that means it is an analog signal. If you see n here, then that is a digital signal. That is how you have to identify. T, it is analog signal, n it is a digital signal. So it is an analog signal. So this is how it is defined. That is, u of t is equal to 1 for t greater than or equal to 0. For t greater than or equal to 0, the value is 1. Otherwise it is 0. For all values of t less than 0, it is 0. Now, this is the mathematical definition of that unit step function. We'll see the diagram. So this is how it looks like graphically. When you see graphically, you will understand the mathematical expression or the definition in a better way. That is, from t is equal to 0, the value of u of t is 1. The magnitude is 1 hereafter. For t greater than or equal to 0, the magnitude is 1. For t less than 0, the value is 0. So you can see that the value of u of t has value only from t is equal to 0, and that is a purely a right-sided sequence. Right-sided signal. The values are only to the right side of t is equal to 0. There is no value to the left side of t is equal to 0. So this u of t is a purely a right-sided sequence. Okay, and one more thing. This is a general thing. See, we have seen discrete time signal or digital sequences, and when we have watched that, we have seen that there was a pivot, and that pivot indicated the position of n is equal to 0, where n is equal to 0, points where n is equal to 0 is. But if we have such, so that can be easily done for a finite sequence. There are infinite sequences also. So how can that be done? So that is a point. That's the reference point. N is equal to 0 or t is equal to 0 is the point, is the reference point. Okay. So one thing is that if such a thing is not there, how can you identify where the sequence or signal starts? That is very important. So where the signal or sequence is start, for an infinite sequence. This u of t is an infinite signal. Why I call it as an infinite sequence? You can see that. See, for t tends to infinity, this magnitude remains the same. This magnitude remains the same for t tends to infinity. So that is an infinite sequence. So naturally, the thing is that we have to identify the starting point of u of t. The starting point of u of t. So how can you identify that? You just make a simple understanding. That is the argument. What is the argument? The argument here it is t. So the argument t should be equal to 0. That is the point where argument should be equated to 0, and that is the point where the signal starts. Signal starts where the argument is equated to 0. So what is argument here? The argument here it is t. When I equate t is equal to 0, so the signal starts at t is equal to 0. Now I have another signal here that is again a unit step function, but you can see that it is u of, instead of t it is t minus a. That is, it is argument is t minus a. Now you can see that we have to identify where it starts. After we identify where it starts, we can actually write the definition more clearly. See where it starts. I told that the argument should be equated to 0. That means t minus a should be equated to 0. So when I make t minus a equal to 0, that means that t is equal to a. So the signal starts at t is equal to a. So this is how the signal. So the signal starts at t is equal to a. So this point it starts, and afterwards the value of u of t minus a is 1. Okay, afterwards the magnitude is 1. So how can I write the definition? The definition is u of t minus a is equal to 1 for t greater than or equal to a, and it is 0 for t less than a. Beyond this point, after this point it is 0. From this point it is all 1. Now similarly, you can see what is a digital step function. That is, instead of t you have n, and see the definition. Instead of t, very simple. If you know u of t, it is you can easily understand u of n. That is equal to 1 for n greater than or equal to 0, and it is equal to 0 for n less than 0. So how it is done? See, this is all n. Instead of t you have the baseline as n, and for less than n values less than 0, that is minus 1, minus 2, minus 3 up to minus infinity, there are no values. It's all zeros. But from 1, from 0 it is 1, at 1 it is 1, at 2 is equal to at 2 it is 1, at 3 it is 1, till n is equal to infinity. This u of n has all the spikes at 1. So this is a purely right-sided sequence, and it's an infinite sequence because it extends to infinity. So where is the starting point? The starting point, I told that when it is u of n, when it is u of n, where is the starting point? Put the argument is equal to 0. So n is equal to 0. So this is the starting point. Now similarly, we just take another example, that is u of n minus k. So where is the starting point? The starting point is at n minus k is equal to 0, or that is equal to n equal to k. So you can see that this the signal, that is the starting point is here, and thereafter all samples are having the value 1. All the values are having all the values are 1 here. To the left of k it is all 0. So you can see that the sequence is shifted to the right by k. So that is a delay operation. So the sequence is delayed by k samples. Okay, you can say that the signal is shifted to the right by k samples. If I put k is equal to 2 here, the sequence is shifted to the right by 2 samples. Likewise, you can tell for this one also, that is, if I'm delay, this is a delay operation. If it is t minus a, then the unit step signal is delayed by a seconds. If a is equal to 2, then it's delayed by 2 seconds. Now we'll move on to the next one, that is unit ramp function. So it's represented by the simple r of t. So r of t is defined like this. That is, value is t for t greater than or equal to 0, and it is 0 for t less than 0. Okay. So r of t is nothing but, so you can write it as this way. That is, so whenever you have to ensure that it is a right-sided sequence, so you can see that it's a purely right-sided sequence. right-sided sequence, actually you can write it as r of t is equal to t itself. Simply write r of t is equal to t. The equation satisfies, but you can see that the value is only to the right of t, that is t right of 0, that is t greater than or equal to 0, t less than or equal to less than 0. That means it's a purely right-sided sequence. So whenever you have to ensure that it's a right-sided sequence, you have to multiply that with u of t limit. So we will just go to the waveform. This is the waveform, that is r of t. As I tell, this is a purely right-sided sequence. It starts at 0. Why it starts at 0? Put the argument t is equal to 0. That's the point where r of t starts. And you can see that all along the way, the slope is 1. That is the crux of the signal. The slope is 1. If you take the slope, I hope you know to find the slope. If you take the slope is equal to 1. So r of t is having a slope 1. Okay, now this is a right-sided sequence. So here the value is t, here the value is t, here the value is t. So how can you ensure that it's a right-sided signal? You simply multiply that t with u of t. Now likewise, next one, what is r of t minus a? Put the argument is equal to 0, that is t minus a is equal to 0, that is t is equal to a, that is a point where r of t starts, that is it is shifted by a seconds. It is shifted by a seconds. Thereafter the slope is 1. Now what is the definition here? That is at t minus a, the value of r of t is r of t minus a is t minus a for t greater than or equal to a, and otherwise it is 0. Okay, so how can be written in terms of step function? That is t minus a. There it was t, now it is t minus a. There it was u of t, here it is u of t minus a. Now another relation also, see, okay, I'll come to that later, little bit later. See, okay, then we'll go to the that is digital ramp. That is digital ramp is like this. I'll go to the okay, we'll just see. That is the base is n here. At 0 it is 0, at 1 it is 1, at 2 is equal to 2, at 3 it is 3, at 4 it is 4. It goes like that. Okay, so there it was for analog the slope was 1, but here it's not that way. That is at 0 the value is 0, at 1 it is 1, at 2 it is 2, at 3 it is 3, at 4 it is 4. That is how it moves. So you can tell that the definition, that is r of n is n for n greater than or equal to 0, and it is 0 for n less than 1. Okay, so this is how you hope you understand where it starts. It starts at n is equal to 0, and it is actually r of n is n. It is actually n, but in order to have it as a right-sided sequence, you have to multiply by u of n. This is how it is defined. It's a purely right-sided sequence. In order to ensure that it is a right-sided sequence, so actually by definition it is only n. So this part also should be included. How can you define this part mathematically? Simply multiply n by u of n. So this is n here, n is here. How can you define this one? You are defining this one by multiplying n by u of n. Similarly, you can have r of n minus k. It starts at n minus k is equal to 0, that is n is equal to k. So it has a value n minus k, and its starting point is that is the values will be for n greater than or equal to k, where the starting point is n is equal to k, and it is having a value 0 for n less than k. And also you can tell that instead of n, by definition only this much, that is n minus k. In order to ensure this portion, it should be multiplied by u of n minus k. So this is how. So by definition we can tell that this r of n minus k is shifted by k samples. Shifted by k samples. It is here also. That is, it is delayed. It is shifted to the right by here it is r of n minus 2. That means it is shifted to the right by 2 samples. Initially that should be starting here, but it is delayed by 2 samples. 1, 2 starts at this point. Okay. Now, okay, this is the starting point. Is delayed by 2 samples. 1, 2. It starts at 3. Okay. Okay, there is a mistake here. N r minus n, that is n minus 2 means it should start here. Okay, there's a bit. Okay, okay, okay. Right, right, right. It's correct.